Hello everyone. My name is Zakharov, and today I'm going to present our research paper on optimizing big integer multiplication of Bitcoin, basically introducing the W window approach. So one thing to note is the paper is highly technical, so it just goes on with various algorithms for optimizing the multiplication of Bitcoin. So I'm not going to go into low-level details in this presentation on our approach, but give like the overview of what we have achieved, why we decided to take on this project in the first place, and see the high-level idea of our optimization. So this is a joint work on distributed lab and Alpen labs. You can see our implementations here in the paper here. So in case you're interested, you can read it in more detail. So first, let's begin with the introduction to Bitcoin script and why do we even need Bitcoin script at the first place. So the Bitcoin script is essentially a scripting language which is used in Bitcoin to specify conditions on how you spend the UTXOs. So essentially, this is the way how the financial side of Bitcoin is functioning, and this is what restricts everyone from using someone else's coins besides theirs. So probably the most popular example of the Bitcoin script is the so-called pay-to-pub key hash. And so when you specify the conditions for UTXO models, you have two parts. The first part is the pub key. So this is the condition which basically specifies how you can spend the UTXO models. And then in order to spend the coin, you need to provide the script seek, which is basically the values which you need to provide in order to this condition to be satisfied. In this particular case, the script pub key is the script which basically allows you to spend coins in case you have the signature corresponding to the hash value of the public key, which is published on chain on Bitcoin. So now to introduce the notation a bit and to give a grasp of how Bitcoin script is operating, let's give the example of spending the coins using the pay-to-pub key hash script. So suppose that we provided the valid signature in the public key, and then we concatenated the part which basically stands for the condition for spending the coins. Let's see how the script gets executed. So first we add signature in the public key to the stack, then using the opcode, so these are opcodes. So using opdup, for example, you duplicate the public key, which lies on top of the stack. Then you hash it using hash 160 function, so this opcode right here. Then what you do, given two hashes, you can basically verify whether they equal or not. So you do this by using the op equal verify opcode. In case everything goes well, these just get eliminated. In case these are not equal, the script aborts, so you cannot use the coins. And then finally, once you have the signature in the public key, you can use the keyword check signature to spend the coins. In case everything goes well, you get one. And so you can spend the UTXO model if and only if the output of your concatenation of the script signature and script pub key gives you one. Okay, so with these tools, basically the Bitcoin script allows writing only basic smart contracts using only native opcodes operations. So for example, you can easily implement the hash preimage verification. So for example, given the hash value, you might want to spend the coin only if you have, say, the message, which by hashing gives you the value which is provided in the script signature. You can also implement time locks. So for example, you can spend the coins only after some period of time. You can also use some basic signatures. These are ECDSA and Schnorr for Taproot. You also have threshold or multi-signatures implemented on top of Bitcoin script. And that's pretty much it. So you can actually use some combination of those. You can, for example, lock your coins on multi-signature, or you can spend it after some time. And you can specify these and/on and or conditions for your script. But that's very limited. Can we implement some non-native verifications? And that's basically the question which is asked for majority of current Bitcoin research. In particular for BitVMâ ecosystem. So the BitVMâ tries to actually implement L2 over Bitcoin. And in order to do that, you need to implement some more complex verification mechanism in Bitcoin. So for example, you might want to implement ZK snarks, such as Grot16 or Flonk. You might want to implement ZK snarks or even BLS signatures. So can we actually implement those? And technically we can. These scripts will be, of course, really big in size, and current research efforts are to build the system which is able to verify these computations by not running the whole program, but still you have to write the whole program in Bitcoin script nonetheless. So the Grot16 is surprisingly implemented, and you can actually check its implementation in the BitVMâ repository. You also have Flonk, which is basically the Plonk-based system, but with a bit more effective verification than Grot16. For example, such systems such as ZK Starks cannot be currently implemented. That's because in the Bitcoin script, you are so limited that you cannot even concatenate values inside the script. And so for that reason, you do not have any advanced techniques in zero knowledge, such as Dmytro transformation or even Merkle trees. So they are not allowed in Bitcoin scripts, so you are pretty much limited. So you cannot implement code-based zero knowledge systems. Yet there are also a part of the research community which tries to research what happens if opcat suddenly becomes active in Bitcoin script. So what mechanism can you implement? And it turns out that the circle Stark is also already implemented, but assuming that opcat is present. And also, you pretty much, theoretically, again, you can implement any discrete log-based protocol that does not involve hashing. This might be Sigma protocols, bulletproofs, BLS signatures, etc. So in other words, currently it is theoretically possible to beat Grot16 ZK snark verification in the following form, where you can, in the script, publish the proof, the fallback statement, which corresponds to the proof, and then do this op check Grot16 kind of opcode. But here, what we mean is the implementation of these protocols. And so, yeah, the core problem currently is to make this implementation optimal. And one of our goals of our research is to actually make it optimal. So what did we do for that? So let's first consider what are the problems at all with implementing mathematics in BitVMâ and in particular in Bitcoin script. First, the arithmetic is allowed only over U32 integers. So you're not allowed to natively, say, publish some 256-bit integers. You're only restricted to U32. From arithmetic, you can only use very basic operations. This might be addition, subtractions, negation, absolute values, some comparison opcodes, but that's it. So you cannot even multiply to U32 integers. You're very limited in this sense. The flow control is also very limited. So you can write if statements or else statements, but that's it. So you cannot, for example, do the for loop. For that reason, the Bitcoin script is not Turing-complete in particular. So you cannot do any for while loops. But in case you know the length, say, of the for loop, you can actually use it, but that's just going to be a repetition some number of times. So currently, the big integer multiplication takes roughly 75,000 opcodes to implement. And so the goal of our research is, can we implement a better approach? And as it turned out, besides basically optimizing the multiplication algorithm, we also, our approach allowed to optimize some other protocols as well as a result. So now let's go into some high-level details of the approach. So first of all, we need to determine how to even represent integers in Bitcoin script. And so we just use, so recall that an integer can be expressed uniquely in arbitrary base b. So this is going to be a sum in this form. So we will call each xyots, which are restricted from 0 to b, as limbs. And the number of limbs is just basically the limb size of x in base b. So yeah, if we choose b to be small enough, so in our particular case, less than 32-bit integer, then we can publish individual limbs to represent the x. So instead of just pushing the whole integer into the stack, we're going to push individual bits and then just somehow process them. and we chose the power of 30. So essentially, we represent each integer as the set of 30-bit chunks. And then we implement every algorithm we needed, like additions, multiplications, etc., using this representation where we basically split the whole integer into 30-bit chunks. Okay, so let's give an example just to be more specific. Suppose they have this 244-bit integer. And so you cannot just basically take this integer and push into the stack, because recall that Bitcoin can only process integers which are up to 30 bits in the stack, 32 bits, I apologize. So in order to publish this integer, you have to split it into 9 pieces. So they are provided here. So essentially your adding integer script looks as follows. You just publish all these individual pieces of size 30 bits. And surely you need 9 limbs to represent, for example, a 254-bit integer, because 8 limbs would correspond to 240-bit integer, but we need slightly more, so you take 9, and this will correspond to 244-bit integer. Good, so now as a warm-up, let's implement some Bitcoin script to add 2 integers to 244-bit integers specifically. And let's assume for a moment that no overflowing occurs. So you do not get 244-bit integer, for instance. So again, our solution is just to split first the integers into 30-bit limbs. And then, well, as in the computers and how it is typically implemented in the hardware systems, you just basically add limb by limb, starting from the least significant one. On each step, you add 2 limbs together with the carry bit, which starts from 0. Then in case you do not exceed, so this is the resultant bit of the limb of the output, if it does not exceed a 30-bit range, then you just simply set it as t and set carry to 0. In case it overflows, so it becomes larger than 30-bit integer, you subtract 2 to the power of 30 and set carry to 1. And then you proceed with this multiple times. So this is how the low-level implementation looks like. I'm not going to go over this because it really requires the careful reading and the careful manipulation of the stack. But essentially, in case you're interested, you can figure it out how essentially it works. But on the high level, again, this is essentially what we are doing. So essentially, on each step, we have 2 limbs, xn, yn. Then we have the carry c. And so what you're essentially doing, you add in xn, yn. And in case the overflow occurs, you just basically subtract 2 to the power of 30 and set c to 1. And this is encapsulated into the oplim add carry opcode, which we also provided an implementation in the paper. Okay, good. So now the main problem is multiplication. So how do we do it? And the current approach in BitVM, well, at least while we were developing this particular algorithm, was to first decompose one of the integers to the binary form. Then you just go along this binary form. On each step, you multiply some temporary value by 2. And in case you encounter a bit of 1, you add to the result this value of t, which accumulates. And that's pretty much it. So you get the integer r as an output. But here's the issue. Suppose that you have an n-bit integer, so in our case 254. Then if you analyze this segment, you notice that you have to perform exactly n additions and n doublings to implement this logic. And in fact, we noticed that you can do much better with a pretty well-known approach in elliptic curve arithmetics, which is called W window decomposition. So essentially, the W width form of scalar is simply the representation where the base is 2 to the power of W. So that's pretty much it. So with this approach, you have the decomposition of length n divided by v sailed. And so it turns out that instead of NA plus ND complexity, you get a much better complexity. So this complexity is as follows. So you have the part which basically corresponds to the cost of lookup initialization. We'll consider what I mean by lookup initialization in a moment. What's essential here is that this part is essentially constant. It does not depend on the integer representation. And this is typically a really small value since we take W to be 4, in fact. So what's even more important is this part. So again, notice that the number of doublings is the same, but the number of additions is reduced by a factor of W. So in case you set W to 4, you can expect the algorithm to be 4 times more effective than the regular approach, in terms of additions, of course. Okay, good. So what the algorithm looks like, and that's basically the high-level overview of how we have implemented it, is to, instead of